My name is Stephen Moon. I'm a Senior Solutions Architect with the AWS Specialist team here at Amazon Web Services. Today I'm going to be talking to you about some of the database offerings that are announced at this year's reInvent conference. So they come in two different things that I'm going to talk about: new services that were announced and also capability and feature enhancements to some of our existing services. It's going to include talking things about Aurora Global Database, or RDS on VMware offering, DynamoDB Transactional APIs, DynamoDB On-Demand, our new database offering TimeStream, and our new database offering Quantum Ledger Database. So let me start out with Amazon Aurora. So one of the things that we're offering now with Amazon Aurora is global database. Traditionally, database has been via some type of log replication between database instances. What Aurora Global Database is going to be able to do is replicate between AWS regions, so globally, providing storage layer replication. So it's going to be, the use case is going to be for disaster recoverability, predictable low latency geographic read scaling. So again, between regions, not just between AZs. As part of the current general availability limitations, it's only going to be offered on Aurora at the moment, MySQL 5.6, and it's going to only support one readable remote region only, and it's going to be included within several regions. Future releases is going to include multiple remote replicas to include additional regions in the first quarter of 2019. How it works is that an asynchronous redo log stream and dedicated replication infrastructure for outbound and inbound side. And so if you look at this slide, you'll see that it's actually, we keep replication fleets on both sides. And so if you're familiar with our master endpoints and reader endpoints for Aurora, it's going to work the same way. And so it's going to provide a high write throughput of 200,000 writes per second. So it's going to have a negligible performance impact across availability zones. It's going to have a low replica lag of less than 1 second cross-country replica under heavy loads. So I think you've got an availability zone in US East or US West, or today with a new GovCloud region in GovCloud East or GovCloud West, and a fast recovery of less than 1 minute to accept the full load, read-write load in the event of a region failure, which in and of itself is fairly highly unlikely. A new feature for Aurora Postgres is the database activity streams. It is in private preview, and what that's going to allow it to do is stream audit and database activity to common tools that most customers tend to use, such as McAfee Data Center, Imperva, and IBM Infosphere. It streams database activity to Kinesis Data Stream so that any Kinesis client library or consumer library can actually take that stream and perform some type of security analytics. So think in the context of security and incident and event management for some of our government customers, for some of the requirements for the Department of Defense, for instance, for their security mining logging. We also have a new feature called Cluster Cache Management. And what that's going to do is it's going to keep a read replicas cached in sync with that of the primary node. So typically when a node fails, the cache has got to heat back up or rehydrate itself on the instance that is brought up to take over for the fail node. In this case, the caches are kept in sync so that there is no rehydrating. So it provides high performance immediately after failover instead of having to wait for the cache to repopulate itself. Again, as in all, the storage in Aurora is decoupled, and so that cache is kept in sync at the database layer. We have Outbound Replication new to Postgres Aurora as well. So it's going to add support for Postgres replication slots in Aurora PostgreSQL. So it's going to allow customers to use standard Postgres logical decoders. So you think the difference between physical and logical database replication. Logical replication generally means applying SQL statements that are generated on the primary and stream those changes to target SQL to JSON, test decoder, decoder raw. And also customers can use replication tools now, such as DMS, our database migration service, to replicate changes to other database engines. And so if you've got an Aurora PostgreSQL database, now you can use DMS to not only populate target databases, but also to use change data capture as a method to propagate those changes on an ongoing basis. Amazon RDS on VMware is a new offering that is building on our current relationship with VMware for running VMware in the cloud or running VMware and some of our other service offerings, which you'll probably hear about. It's not like Amazon RDS, but it is Amazon RDS in your data center. So again, everything in Amazon is customer-centric. So this is driven by a lot of customers asking us to be able to bring the functionality of RDS into their own data center, for issues such as data sovereignty or application latency in the cases where they want to still run their application on premise, but they don't want to manage a database in the traditional way of having to manage infrastructure, provision, and all that stuff. So all of the provision, patching, monitoring, scale up, scale down, and patching, which is a big plus for a lot of customers, is taken care of in the same manner that RDS is in the cloud as RDS on VMware. And I'll talk about snapshotting, restore, point in time, and availability management as well. It's currently in preview. So how does connectivity to RDS work with RDS on VMware? So you have your AWS region today, and your RDS console is the same. And so all of your functionality and things that you'll be doing in your RDS console is going to work the same way with RDS on VMware as it does with RDS in AWS. The VMware vSphere cluster in your own data center is actually creating a new concept called a custom availability zone. And so a customer would go in and define, as part of their RDS setup, a custom availability zone. And once they've defined that a custom availability zone, they get a download to actually deploy the configuration, the virtual machine on their on-premise in their VMware cluster. And then they would go back in their AWS console and configure things such as IP address, VPN tunneling, different things that are part of that configuration setup. And so that connection is over a VPN connection. It could be over Direct Connect to a DMZ that is set up for the customer by AWS on their behalf. The customer would download the connector into their own VMware environment, as I mentioned earlier. And that connector is going to handle control traffic and different things that are going to be used by RDS on VMware from the AWS management console. So as I mentioned before, all of that traffic is going to be pushed down through the VPN connection for management plane activity, not database activity. And then the metrics that are going to be collected as part of that are going to be pushed back up to AWS. So anything that you want to push to S3 or CloudWatch metrics or anything like that are still going to be pushed back to AWS so that you can use your AWS tooling to do all of the same features and functionality that you were doing previously. So provisioning and management. And so in a customer's data center, I mentioned you download the VMware connector, install it on your VMware cluster in your own cluster control network. And what that cluster control network is a control plane similar to the private control plane that's used in AWS for your VMware cluster. And so an RDS instance is dual homed, meaning it exists in its own private virtual private cloud for management and other activities that are done as part of our shared responsibility model. And then there's the application network, which would be akin to a customer's VPC, in which that RDS instance exists from a connectivity standpoint. And so within that cluster control network is going to be the RDS control virtual machines and the VMware control VMs that are going to act on behalf of the AWS management console to manage your RDS solution on VMware and in your on-premise data center. So again, just like you would in any other an RDS deployment in AWS, your MySQL or Postgres or SQL Server databases are going to be dual homed in the private management network that's owned by AWS and your application network, in this case, a VMware vCenter cluster. And then your applications connect just like they would in the AWS environment. So backup, restore, and read replicas. Read replicas are created just like they are in AWS. And so a read replica from a master instance, you can create multiple read replicas just like you can in AWS. You can also restore a read replica just like you can in RDS and AWS. One of the things to remember about a read replica is it is an actual restore of the data to its own database. And so that read replica can be built as it was at the point in time from which it was created, or it can also be built from a point in time snapshot. So let's say you have multiple read replicas and you only want to see things from, you want to see something from 7 hours or 7 days, 3 hours, and 47 minutes ago. You could restore one of those read replicas to that point in time to do whatever it is, if it was for auditability or for some other reason that required as part of your operational mission. Some of our database instances, Postgres and MySQL, for example, also support read replicas for reader endpoints, which is also supported in RDS on VMwares now. So again, it's created the same way that you would through the RDS management console, and then the control traffic is propagated through the RDS connector, RDS on VMware connector, and then the controls are issued, the commands are issued, and executed in your on-premise environment from VMware. So one of the things that's coming is really interesting is hybrid management. Let's say that you have a VMware cluster and your master is there on-premise and you create a couple of snapshots. But let's say you wanted to create a bunch of snapshots, but you didn't want to store them all on, maybe more expensive hardware or storage on-premise. Some of those snapshots could also be stored in AWS. You could store hundreds in AWS. Really, there's really no limit to the amount that you could store depending on, what your operational mission requirements are. You can also deploy read replicas across multiple, we would call AWS regions or custom regions in this point for your on-premise data centers. And so you'll be able to deploy a read replica in AWS, also a read replica, let's say in another data center somewhere that was geographically separated, as long as that connectivity is available. And then the latency between data centers, between your on-premise data centers, will determine how well that lag between those data centers, between those databases can keep up with itself. And so database engine support happening now. We've got support for Postgres, MySQL, and SQL Server 2017, which is coming soon. For general availability, we're going to have support for Postgres SQL, MariaDB, MySQL, and SQL Server. Soon thereafter, Oracle. So looking forward, I mentioned hybrid snapshots, data center to data center, data center to AWS, and restore a new RDS database in any region. Talked a little bit about hybrid read replicas, so data center to data center to AWS, disaster recoverability, geo-proximal read. So if you want your customer base or your user base to log into the closest region. So let's say, GovCloud East or GovCloud West. That's also possible. And then, migration, one-click promotion, Oracle support, and cross-customer or cross-cluster high availability. So next is really to look at your applications and say, of all these things you're doing, what's the most beneficial to you? So the next thing I'm going to discuss is a couple of new features in Amazon DynamoDB. So one of the interesting things, and for those of you, DynamoDB is our NoSQL solution service, serverless solution for transactional applications. And so one of the things that's always been problematic or challenging with traditional NoSQL environments is the fact that all of any kind of ACID transactions, so if you think about traditional RDMSs, ACID transactions, atomicity, consistency, isolation, and durability, had to be managed on the client side, meaning client code had to be written and every application had to account for the fact that their particular OLTP system perhaps may need ACID compliance. What DynamoDB Transactional APIs does is it takes that and puts that on the server side. And so it just becomes another API call for the custom application to enable an ACID compliant transaction. So a little bit of use cases for those financial applications, so banking applications or any kind of financial ledger applications where that transaction has to be consistent, durable, and all the things that are applied through ACID compliance. Process orders, coordinate in multiple player game scenarios for more kind of the gaming industry. Metadata about distributed systems. So there's a lot of use cases, and the reasons why RDBMSs have persisted for a long time is the fact that they implement ACID compliance, and it's very important for transactional systems for a lot of reasons. So some of the key features I mentioned, it provides ACID for DynamoDB for multiple transactions. You can perform transactions both within and across multiple DynamoDB tables. And that kind of gets into a little bit about what's the best design for Dynamo. Typically, one DynamoDB table should support your application. However, if for some reason it does not, you can span that transactional API across multiple DynamoDB tables. It's a native server-side solution that provides better performance and cost than client-side libraries. That's a key point because having it server-side means that it decouples that requirement from your developers so they can focus on developing applications, not on developing logic for transactional atomicity. So I mentioned that some of the development simplifies the developer experience of making coordinated, all or nothing changes to multiple items. It extends the scale and performance and enterprise of DynamoDB to a broader set of workloads. So it really extends into workloads that I mentioned before that really require transactional consistency across a broad user base. Because you don't want users updating records in a non-way that can disrupt other user transactions. And that's really what the problem this is solving. So some of the traditional challenges of using transactions with a non-relational database, so a NoSQL database, creating and maintaining your own transaction client library, you have to write code to build all that logic in, and to modify your application to logic to work around a lack of native transaction support. So why developers need transactions? I mentioned simultaneous writes or updates to multiple items. DynamoDB has always had consistency with a single write. So this is focused on not only multiple writes, but multiple gets, and I'll talk about that in a minute. Check multiple conditions while executing an action. So in any kind of ACID compliant database, there's going to be conditions that have to be met in order for that transaction to succeed. If it doesn't succeed, it's going to send a notice back to the user to say that this condition was not met, and therefore the transaction cannot continue. And ensure data is consistent across multiple tables. Again, this is the design feature. Do you need one table or multiple tables? I would say that a lot of DynamoDB applications only require one table. But if your application requires multiple tables for whatever reason, then it supports multiple table transactions. So it is a single API call. So it's an all or nothing action within and across tables within a single API call. And I'll talk about each one of those API calls next. So transaction write items and transaction get items are the new API calls. So traditionally it was a get item or a put item for a single item, right? So an item being synonymous to a certain extent to a row in an RDBMS. So a customer record might be an item, or a transaction might be an item. So these are new API calls that allow you to send multiple items. Right now it's up to 10 items in a single call. And so you can write 10 items in a transactionally consistent manner across to a single DynamoDB table or across multiple DynamoDB tables. The transaction get items is more around seeing multiple items in a consistent state. And so what I mean by that is that traditionally if I had to get 10 items, let's say, and then look at those items, I had to get each item individually. And then as I was getting those items, an update to an item might have happened in an inconsistent manner with other items that I was getting. And so I would get that view in an inconsistent state. A transaction get item API allows me to get those 10 items in a single call so that it's a consistent view, a consistent state across those. So I mentioned atomicity, consistent, isolation, durability. The other thing it's talking about is it's idempotent. So it's tokenized. And so what that means is if I execute something, subsequent executions are going to happen the same way. That doesn't necessarily mean that I'm going to retrieve the same information, but I'll get the same result. And that's very important. They're synchronous, which is important to point out. It's not an asynchronous call, it is synchronous. And so it requires 2 write or read units in order to execute a transaction. There are conditional checks, and so it's going to look for different things as part of that transaction to see whether or not that it's a valid transaction, it's going to be committed. We have, recently 99.9% SLA with DynamoDB. Performance is going to be predictable because it's going to scale. It is Dynamo, so it's going to scale like any other implementation would. Without the ugly, so you don't get deadlock. So it uses an optimistic locking mechanism. So if you're familiar with optimistic versus pessimistic locking, pessimistic locking assumes that somebody else is going to do something with that data and therefore locks that particular data item while somebody's transacting against it. That's not good in a high transactional system when you don't want to put a lot of locks out there because that can cause deadlock issues. Optimistic locking assumes that you're going to be able to perform. It really decouples the performance of the transaction from the actual committal of the transaction itself. So that's where the conditions come into play. As it is optimistic locking, which means it doesn't lock the item. And when a transaction API is issued against that to commit the transaction, then it actually allows it to proceed, or throws back an error code and say, no, it didn't proceed because, or did not commit because it did not meet that condition. No long running transactions, unmanaged concurrency, and then, the DBA pain and suffering, that's managed by DynamoDB itself. So it's not only the fact that your developers don't have to worry about it anymore. Writing client-side libraries, your DBAs don't have to either. So DynamoDB On-Demand is another feature to further expand the portfolio of our serverless offerings. And so Dynamo has always been serverless in the sense that the customer is not managing servers, but what they are managing is capacity. And typically they provision write capacity units and read capacity units to scale their workload. And so now you can think of DynamoDB as having two different choices for customers. You can have a pure on-demand, or you can have a provisioned model where you provision a certain amount of write and read capacity units for your particular application. It's not a right or wrong answer. It's whatever fits your need as the customer. And so what's nice about DynamoDB, though, is you don't have to think ahead and try to figure out what is your provision capacity going to have to be for that particular application. You can start at 0, and there's really no limit because you think about how DynamoDB scales. So there's no capacity planning, provisioning, or reservations. Simply make the API calls. You pay only for the reads and writes and what you perform. So one of the things that people would ask is, why would I just not do this instead of provisioning capacity units? And it is a little bit more expensive in a pure on-demand model versus a provision model. And generally speaking, a lot of customers use a hybrid of both. And so if you think about how you would provision EC2 instances, maybe with reserved instances and a combination of reserved and on-demand instances, kind of the same principles apply to this, as a lot of applications will function in a hybrid type manner. And so it eliminates the trade-offs of over or under provisioning. I mean, it instantly accommodates your workloads, traffic ramps up and down. This is just explaining, now the difference between provision now and auto-scaling and set a minimum, where that minimum and maximum is no longer applicable. And so this is one of the features that a lot of customers wanted, and it really is, one of the cooler service offerings, in my opinion, of DynamoDB that was announced this year. So Amazon TimeStream. So this is a new service that was announced this year, and it's a managed time series database. So the question is, what is a time series database? Why can't I store time in a timestamp field in my database, or a sysdate in my database? You can, but there's reasons not to. So what is a time series, right? What is time series data? It's a sequence of data points recorded over an interval. So anything that has to do with time, right, recorded over intervals. So you can think of stock quotes, right? They're recorded probably at the second or microsecond level. Temperature, precipitation, humidity, everything that has to do with environmentals is recorded over time. Even within Amazon, we record within our own data center, within our own fulfillment centers. Everything is time. So we're constantly looking at data that has a time component to it. And so what is special about a time series database is time now is the single primary axis of the data model. So you think about of your data model, you don't have to take that into account as far as allocating specific resources, because it's a known quantity. And so time series use cases for humidity, for instance, what does it look like over time? I've got application events, I've got IOC sensor readings, I've got DevOps data. Or for instance, fast moving time series data from multiple sources at a rate of 1 million inserts per second. So from a performance standpoint, again, because it's a known quantity of time, I can purpose build TimeStream to accommodate for that. I can trillions of events daily, right? I can capture pretty much an unlimited amount of events. Analytics are optimized for time series. So just like other database functionality, you've got two different types of thoughts in the database world, of multimodal or purpose-built. And so this is a purpose-built database, which allows it to be tuned for a very specific thing. And other database offerings, such as Neptune, for instance, are tuned for or built for understanding relationships between things, and it's tuned specifically for that. One of the really interesting things is being able to interpolate missing data. So one of the problems with feature engineering a lot of times when you talk about machine learning and data science is missing data, and how do you interpolate data? And so actually with TimeStream, it actually interpolates data for you. So interpolation being adding data points between two data points that are missing, versus extrapolation, which is predicting data points based on the data points that you already have. And so it takes a lot of, again, it's one of those things that takes a lot of the work out of the machine learning realm and automates that for you. And it's serverless. There's no servers to manage, so you're not doing all the things that you typically would do with any database server for that matter, or any server. You're not provisioning and all that stuff. And so again, it's purpose-built based on customer demand. So Amazon Quantum Fully Managed Ledger Database. So this is also a new database service that we've announced at reInvent. That is a ledger database. And so what is a ledger, with centralized control? So what does a ledger do really? Well, a ledger is really for verifiability of transactions. And we'll talk about kind of the most common. Everybody talks about Bitcoin and some of those other things that are, but the key difference is this is centralized. It's not a distributed ledger. And so for applications like healthcare, where you've got to track, verify insurance, tracking vehicle history, manufacturing, anything that you need a verifiable and auditable transaction trail. The most common is an accounting ledger, for instance. That's where the term ledger comes from. Right? Accounting ledger would be a good example of things that accounting transactions have to be verifiable, they have to be auditable, and have to be traceable. And so the traditional approaches to auditability is they're hard to build. I mean, I've built lots of databases with this type of functionality in it, but it's a lot of custom work to do it. You've got to audit functionality using triggers and stored procedures. And you got to maintain, you've got to build it, you've got to maintain it, you've got to account for the application. There's a lot of work to it. It's resource intensive, meaning that you're spending CPU cycles and really just compute cycles in general in maintaining this and actually executing the auditability piece of the database. Difficult to scale and manage. It's error prone and incomplete, meaning that it is the possibility of introducing incomplete audit records or missing audit records or wrong audit records is a possibility. The most important thing is it's impossible to verify, because in RDBMS and underneath the core, at some point, some DBA or somebody has access to that. So there's no way to verify changes made to the data by the administrator. And that has to do with the data lineage and auditability of it. And so one of the challenges with blockchain and distributed ledgers is it's designed for a specific purchase, which is a distributed ledger, meaning I have a Bitcoin, for instance, and it has to be able to follow me anywhere. That's distribution. Adds a lot of complexity to it. It's hard to use and slow, meaning that in order to do some of when they talk about mining, Bitcoin mining and things like that, it's very, very compute intensive. And so it's not to be able to perform some of the transactions against distributed ledgers. Very difficult to maintain and very hard to scale. The hard to scale really has to do with the computational power required to maintain a distributed ledger. So what does QLDB, Quantum Ledger Database, do for the customer? Well, one, it's immutable and transparent. It's an append-only immutable journal that tracks history of all the changes, which cannot be deleted or modified. And it's important to understand that the customer does not have access to the ledger to be able to do that. The customer gets full visibility into the entire data lineage, but they don't have access. There's no way for a customer to actually go in and change data. It's cryptographically verifiable, and I'll explain a little bit about hash chaining and how that works. But every transaction is run through a hash algorithm to ensure that the ensuing transaction, the previous transaction before the other transaction, has not been changed. And I'll talk about that a little bit too. And it's highly scalable. It's very easy to use. I mean, it's a very familiar SQL-like interface, and I'll explain a little bit about that here in a second as well. So what does a ledger database look like? It's a ledger. So it's going to have, the ledger is just a record of transactions. You enter a transaction, you modify a transaction, or you delete a transaction. And typically a delete of a transaction is not a physical delete. It's just a marking of saying this transaction is deleted. It also compromises the current and historic view of the data. So current being what was the last transactional state of the data. Historic means everything that happened to that particular transaction, that particular piece of data. So how does it work? So I've got a journal, and let's say I want to insert some information into that journal. I insert that information. It creates a hash of transaction 1. That information, and this is not a relational model, it's just depicted that way, so it's for easy viewing. That becomes my current view. It also becomes my historic view because I've only got one record, so historic and current are going to be the same in that sense. Next, I update a record, and I create a second hash for that transaction, which is changed from the first hash, which I'll explain a little more detail in a minute. And then my history changes because I have updated the owner but I've kept it. Now my historical record has two different states of that transaction. So I've got the state 1 when I update it, when I inserted the transaction, and I've got a second state of the transaction when I've updated, in this case, the owner. Let's say that I delete the transaction, or I delete the item, in this case, a car, based on the unique identifier of a VIN from my ledger. So it doesn't actually delete it. What it does is it takes it out of the current, but it keeps the historical record of it. And so I can go back through the entire, and marks it as being deleted, but it doesn't delete the information. It doesn't delete the journal history or anything like that. And again, it's a hash and it's chained, and I'll explain that. And so I have a full historical view of a record, transactional record. So how does Amazon verify transactions in QLDB? I mentioned hash chaining. So let me explain a little bit about how that works and why that's important. So when you insert a record, it uses a SHA-256 hash algorithm, which there's plenty of things documented and written about that, so I won't go into the whole explaining how hashing works. But it creates a hash of that transaction, which is a unique identifier for that particular transaction. So that transaction, when I update the records, it also creates a hash, SHA-256 hash, based on that transaction record. But what it also does is it chains or includes the hash from the previous transaction, where the term hash chaining comes into play, so that hash that's generated in the second transaction or the second update includes not only the information that was included in the update, but also the hash from the previous transactions. Again, when I go and delete the record, same thing, change from the second hash, the hash created from the second one gets included in the hash of the third transactions. Now, how does that verify auditability? If I go back and change the record in the original, say I change the name of the owner, it's going to create a whole new hash, unique hash from the function, and that's going to carry through all the transactions, so that the original hash that was generated is not going to equal the hash that is generated through hash chaining if any of the records have been changed. So if the hash doesn't match the current hash as part of that verifiability, that function, then you know something's been modified with a record. With that, I would like to thank you for watching this video. And if you're interested about any of the new services, features, or functionality that I've talked about as part of this presentation, please reach out to your AWS account executive or your AWS solutions architect.